Let's have a look at worksheet number 11, questions 1 through 8 right now. For all of these ones, we're going to use the hand rule for deflection. If you remember, the wire grasp, well, the first one we learned in this unit, was used to find the direction of the magnetic field caused by a moving charge. No external field, no force, nothing like that, just a moving charge. Which way does the field point? Thumb, fingers are curved, okay, your fingers point in the direction of the field. Now, the second rule we learned, the coil rule, was exactly the opposite. It was still thumb and bent fingers, but this time our fingers pointed in the direction of the current and our thumb pointed in the direction of the field inside the coil. Now, that third rule that we learned works only if and only if the charged particle is moving perpendicular to a magnetic field, an external magnetic field. Got to be perpendicular, right? That big word, perpendicular, that we're going to see lots through this unit and the next unit. It's so big, it's such an important word that they made it 5 syllables. That's how important that word is. Everything from here on out pretty much is perpendicular. Charged particle moving this way, magnetic field this way, the force is going to be either this way or this way, perpendicular to the way the particle is moving and perpendicular to the field. If the charged particle is moving perpendicular to the field, we can use the hand rule for deflection, and in that rule we're going to say thumb in the direction of the particle, fingers this time straightened out for the first time in the direction of the external field, palm is going to point in the direction of the force. For all of these questions, we're going to use that hand rule for deflection. Number 1 says an electron means it's a negative particle, we'll use our left hand for this, travels to the right of the page through a magnetic field that points into the page. Are they perpendicular? To the right of the page, into the page. Perpendicular? Yes, which means we can use the hand rule that we learned about, right? So let's do that. Left thumb to the right of the page, fingers into the page. For me, it looks like this, right? But for you, it looks like this. Thumb, fingers this way. That's okay, it doesn't matter. In either way, if you look at your hand, Evan, you look at my hand, they're both pointing toward the bottom of the page. Don't say down, say toward the bottom of the page. 2, another electron travels into the page, so thumb into the page, external magnetic field that's pointing to the left of the page. Thumb into the page, fingers to the left of the page, palm points which way? Mason? Not into the page, down the page. Don't say down the page or to the bottom of the page. If our page is our frame of reference, then express that as our frame of reference in our answer. If we have north, south, east, west in the question, that's the earth. Use the earth as our frame of reference then. 3, an alpha particle travels toward the top of the page, positive, right-hand rule. Magnetic field that points out of the page. They're perpendicular, we can use the hand rule. Alpha particle toward the top of the page, magnetic field out of the page, palm points which way? To the right. Yeah. Now in this case, David, you said to the right of the page, which is 100% correct. You could get away without saying to the right of the page there, because if your page is vertical like mine is, your page is horizontal like yours is, it's still to the right. Up, down is different, but right, left will still be the same. Like, strictly speaking, you should say it the way you said it, but you can get away without it when you're talking about right or left. 4, an alpha particle, that's going to be a right-hand rule as well. Travels to the, oh, wait a sec, we got north and west this time. The earth is our frame of reference. The answer will not be to the top of the page or to the bottom of the page or into the page or out of the page. The answer will be like up or down. Travels to the north, magnetic field west. Which way is north? Really, like north is like this way. 32nd Street out there goes directly north. So we need to have a line that goes parallel to 32nd Street, which is kind of this way. Well, it's kind of hard to see that, right, to visualize that. So let's just make it up. Let's say this is north. If this is north, we have an electron thumb going north, this way. Magnetic field points to the west. Which way is west? If that's north, then that's west, right? If you look back at that map of Canada that I showed you on Friday, remember that? Right, you picture looking to the top of the map. Left would be BC, right would be the Maritimes, right? So any way you're looking, if you define that as north, then to your left is west. Alpha particle, north, magnetic field, west. Palm points which way? Up. Don't say toward the top of the page or out of the page. Frame of reference is the earth. You could say out of the earth, but an easier way to say out of the earth is just up. Right? 5, an electron, left-hand rule, travels north, magnetic field that points north. Interesting. Electron traveling north, magnetic field points north. How do you do the hand rule for that? Good news is you don't. You don't have to, because there is no force there. There is no direction because there is no force. 6, an alpha particle, that's a right-hand rule problem, travels out of the page, magnetic field that points into the page. What's the force? 0, because they're, is there what? Can't hear you, sir. There is no force, yeah, because they're parallel to each other, right? When they're parallel, there is no force. Perpendicular, use the deflection rule. Parallel, there is no force. In between, don't worry about it. You're not going to see it. Okay, 7 and 8. 7 says an electron traveling to the east experiences a force to the north. What's the direction of the field? So we're working kind of backwards here. Instead of thumb, fingers, which way does my palm point? It's thumb, palm, see which way my fingers point. An electron is a negative particle. So it's a left-hand rule. This is north, this is east, this is west. Electron traveling east, magnetic force north. What do I have to point north? Fingers or palm? The force is north, so David, you're right, it's the palm that points to the north, right? Thumb to the east, palm to the north. Which way do my fingers point? Up. My fingers point up. The magnetic field is upwards, out of the earth, up, not toward the top of the page. At 8, an alpha particle, right-hand rule, traveling into the page, experiences a force to the right of the page. Thumb into the page, force, palm, is to the right of the page. Fingers point which way? Top of the page. My frame of reference is the page again, so I have to say not up or not forward or whatever. It's toward the top of the page. Let's take a look at number 10 as well. Number 9 we'll skip, we'll do number 10 here. Number 10 says an electron traveling at this speed through a magnetic field, a perpendicular magnetic field, which means everything that we've learned, hand rule equations, is valid. What's the magnetic force acting on the electron? What's the acceleration of the electron? The magnetic force is pretty straightforward, right? We should say F is equal to QVB for this. What's that little upside down T mean? Perpendicular, right? Perpendicular. It just means that this equation is only valid when the particle is moving perpendicular to the field. Charge here is, what is it? It is an electron, so it's 1.60 times 10 to the minus 19 coulombs. V is 6 times 10 to the 5 meters per second. And B is 5 times 10 to the negative 1. When we solve for this, we get a force of 4.8 times 10 to the negative 14 newtons. There's the magnetic force. Should be 4.80, I think, actually, to 3 digits. There's the force. Now, what would Yoda say? We want to find the acceleration. The force needs to be with you. It is. What does Yoda say to do with the force? Yeah, divide by mass. So we'll take that value for the force, we'll divide it by the mass of the electron, and we get an acceleration of 5.27 times 10 to the 16. Oops. That's a pretty big acceleration. Is that possible? Yep. The biggest speed we can have is 10 to the 8, but there's no upper limit to acceleration. Yep.
So how do you get kilometers per second times meters per second times Tesla to turn into?
How do you get?
Like basically.
Oh, I see. I see what you're saying. To turn into newtons. Number 12. An alpha particle initially accelerates at this rate. What's the initial speed of the alpha particle? Well, let's just say kind of the other way around here. We can find the force using m times a, right? We have the acceleration, we have the mass of the alpha particle. 6.65 times 10 to the minus 27 kilograms times 8 times 10 to the 13 meters per second squared. I'm not sure what we get there. But then once we get that, we're going to say F is equal to QVB. And V is equal to F over QB. So we take that force that we just found divided by the charge times B, and we get 5.54 times 10 to the 6 meters per second. Now, I'm going to tell you something here that is going to lead us into what we're going to do next after our break here. This question should not really say the initial acceleration or the initial speed. It should say the acceleration and the speed. Why? Well, how the speed, I'll tell you now that the speed doesn't change. It's not an initial speed, it's the same as the final speed. The speed doesn't change. How can this charged particle accelerate, but the speed doesn't change? How's that possible? You guys learned this in Physics 20. Not in this context, but yeah.
Accelerating in a direction different.
Good. It's changing direction. It's changing direction. So remember that. After a break, we're going to come back and look at the path of a charged particle in a magnetic field. As a charged particle goes through a magnetic field, it will not speed up or slow down. In an electric field, it does. It speeds up and slows down. But in a magnetic field, the charged particle will not speed up or slow down, but it will accelerate every time because it will change direction every time. We'll see what that means in terms of the overall path once we come back from our break.